this is particle. And then we cannot just directly measure atoms, but rather we can assess the number of atoms by assessing masses and moles. So the same 1 mole of an element, whatever it weighs, is the molar mass.
I want to know the number of moles that is represented by the mass given. So the mass given was 4.9, the molar mass is 98. Therefore, N is equal to 4.9 divided by 98. This will give us
1:1. It's just like as 12 represents dozen, 6.02 times 10 to the power 23 represents moles. And when I say now dozen mass, it's just the mass of 1 dozen. And when I say molar mass, it's just the mass of 1 mole in that context. Occupy a volume of 22.4 dm cube. So your job is to find...
You know just what you do. You do.
Alright, welcome to Sa Majesty's World Science channel. This is class 5 of the JAMB syllabus in chemistry, and we'll be handling mass and volume relationships. This is otherwise known as stoichiometry. So permit me to give you a brief introduction to this topic, because this topic is all about calculations. But one thing is that we have to understand the concept we are talking about. So when we say mass and volume relationship, okay, when we say mass and volume relationship, we can otherwise see it as stoichiometry. So when one hears mass and volume relationship, the first thought might be of density, which is correct in the context of chemistry and some aspects of physics, of course, since density is defined as mass per unit volume. So, however, in this topic, mass and volume relationship, will be focused on how the mole plays a critical role in determining the quantities of particles involved in a chemical reaction, expressed in terms of their masses and volumes. So this ensures accurate proportionality between the reactants and the products. So the aspect of chemistry that is concerned with the proportionality between reactants and products in a chemical reaction is called stoichiometry. So what is stoichiometry? By definition, stoichiometry, let's consider the origin of the term stoichiometry. It is derived from 2 Greek words, stoichion, which means element, and of course metron. Anything metri is measure, which means measure. So literally, stoichiometry means measurement of elements, or to measure matter. In chemistry, of course, stoichiometry is defined as the relative proportions in which substances react or in which elements combine to form compounds. It studies the quantities, the quantitative relationship. And when we say quantitative, how can we measure quantity? Mass and volume. So it studies the quantitative relationship between reactants and products in a chemical equation. For us to measure anything, we must introduce a standard and a fixed unit from which other variables depend on. To measure elements invariably involves measuring the number of atoms and molecules present in a given quantity of an element. If we can measure an element, then we can equally measure compounds and molecules, since elements constitute compounds. In stoichiometry, as you can see, the fixed unit of measurement is that the fixed unit of measurement used here is mole. It is believed that you have the idea of mole and Avogadro's number earlier, maybe in your 10th grade. In your 10th grade, that should be your SS1. Other variables such as the number of particles, the mass and volumes of particles involved in a chemical reaction depends solely on the mole. Thus, the mole ratio of the reactants and products in a balanced chemical equation of a given reaction practically represents the stoichiometry of the reaction. Okay, let's relate mole ratio to our everyday life activity. Outside chemistry, let's consider cooking and baking. In cooking, and baking, remember, I'll come back here, but you need to, mass and volume, but you need to understand this I'm saying so that you can grab the concept. When we say mass and volume relationship, the central unit here is mole. So let's say in cooking and baking, ingredients are added in the right proportion to give the desired taste and food quality. If not, the food will not be the food will either be salty, tasteless. Then to keep the good taste of the food you cook constant, you must follow a specific proportion of ingredients with respect to the quantity of food you are cooking. So you must maintain the proportion of the ingredients with respect to the quantity of food you are cooking. Imagine this. Wow, I love the taste of that rice you cooked on your birthday party. Can you please cook the same food for my graduation party next week? You have to remember the quantities of each component you used in the cooking process. For instance, 5 cups of rice, 3 cups of Maggi seasoning agent, 1 spoonful of salt, 1 sizable onion bulb, 1 sachet of kitchen glory, etc. On my graduation, maybe you are to cook 15 cups of rice. At this point, you have to use more ratio of 5:3:1:1:1 respectively for rice, Maggi, salt, onion, and kitchen glory. Remember, why is it 5:5:5? In that ratio, 5 cups, I use 2 or 3 cubes of onion, whatever. This whole thing will be clear when I write it on the board. The amount of quantity of rice you are cooking determines the number of seasoning agents you will use to keep the taste. Remember, I love the one I ate on your birthday. So to bring this up to reality, mass and volume relationship is all about stoichiometry, which measures the relative proportions in which substances or elements react. For us to measure anything, we must consider the central unit, mole. So mole is in the center here. Mole is the determinant. So both mass and volume here depends on mole. I have treated a video on this stoichiometry before, but I still want to do more on this, at least giving you this little relationship in real life situation, what mole is all about. Then from mole you can determine what mass. So, and from stoichiometry we talk about how to measure elements. So in this 1 mole, first of all, a mole is the amount of any substance that contains Avogadro's number as its elementary particles, at its building particles, at its formula units. So any amount that contains Avogadro's number, and Avogadro's number is 6.02 times 10 raised to the power 23. This is particle. And then we cannot just directly measure atoms, but rather we can assess the number of atoms by assessing masses and moles. So the same 1 mole of an element, whatever it weighs, is the molar mass of that element or of that substance. So we have seen mass now. The same 1 mole of a gas at STP will occupy a volume of 22.4 dm cube. This is at standard temperature and pressure. But you know, African, we are funny. Our temperature can never be STP. So the correct thing is that we're supposed to be using at what? RTP, room temperature and pressure. 1 mole of a gas will occupy 24 dm cube at room temperature and pressure. So maybe with time, the exam body will recall and come back to their normal senses. Okay? So you can now see that the central unit here is mole. And remember, this is just 1 mole. So it means that whatever 1 mole weighs is molar mass, and whatever 1 mole of a gas occupies at STP is called gas molar volume. So this over here can still be called gas molar volume. Understood? So this is the relationship showing you that mole is the central unit, is the thing that connects mass and volume. So as they behave in mole, will they behave in mass and volume? So the fixed unit we use here is mole. From mole, we can now move to other units. And remember, this movement is also allowed. One can move from volume to particle, and from particle to molar gas volume. It is also possible we move from particle to mass, from mass to particle. It is also possible, I think these are the possible things that is common. So other ones are there. If it is in electrolysis, we are dealing with 96,500 coulombs of electricity per mole of electron. This is for electrolysis. this is. Okay, so there is no distance that is okay. The another thing is that we can move here. Yes, can move from volume to molar mass and move from molar mass to what? Volume. Now, this is the connection which shows that mole connects mass and volume. So when we say mass and volume relationship, we need to consider the concept of mole. And mole is the amount of any substance that contains Avogadro's number as its formula unit. And Avogadro's number is the number of carbon atoms in 12 grams of carbon 12. So 12 grams of carbon 12, whatever it contains, which is equivalent to this, is what we call Avogadro's number. So we have introduced this. With this, you can now solve questions involving mass, volume, mole, particle, particle mass, particle volume. For instance, if I ask you, how many moles are there in how many moles of gas are there in 3.01 times 10 raised to the power 23 molecules of gases? How many moles are there in these molecules of gas? Look at the fact. 6.02 times 10 to the power 23 is equal to 1 mole. Therefore, this is equal to how many moles? You see how it is working. So just see the explanation. If you don't understand how I'm solving, not the thing I'm solving. Remember, my question is, how many moles are present in 3.01 times 10 to the power 23 molecules of a gas? Always know that over here represents particle. How do we know particles? When we say molecules, when we say atoms, when we say ions, all of them fall into particles. And my question now is, how many molecules, how many moles are present in 3.01 times 10 to the power 23 molecules? So I'm relating 1 and 6.02. 1 is for mole. 6.02 times 10 to the power 23 is equivalent when we speak in terms of particles. If this is even atom, you will still answer the same thing. Now, guess, what if the next question says, how many atoms are present in 12 grams of magnesium? Assume the question is, how many atoms are present in 12 grams of magnesium? How many are present in 12 grams of magnesium? Watch this. Simple. This is gram, which is talking about mass. And this is atoms, which is talking about particles. So your job is to find out. They will give you in the question that mg is 24. This 24 means molar mass. 1 mole of magnesium will weigh 24 in terms of mass. And this 24 grams in terms of magnesium will contain 6.02 times 10 to the power 20. So you will relate this mass and the particle, because the question is now asking you gram. That's mass, and then particles, which is atom. The other first one I asked was how many moles are in, so which means mole and particle. You get that now. So what will you solve here? The answer to this one, the first question I asked, how many moles are in 3.01 times 10 to the power 23 molecules of a gas? The answer is 0.5 mole. If you do your mathematics, if this is equal to 1, this is equal to x. So permit me to clean off here so that I can solve quickly. The simple solution is, you say that 6.02 times 10 raised to the power 23 contains 1.0 mole. That's the reason for this thing I drew here. Contains 1 mole. Then 3.01 times 10 raised to the power 23 will contain x. If you cross multiply, you have that x will now be equal to 3.01 times 10 raised to the power 23 all over 6.02 times 10 raised to the power 23. At the end, you get 0.5 moles as your answer. Okay, then for this one, they say how many atoms are present in 12 grams of magnesium? We are looking at particles and mass. So we find the molar mass of magnesium. Remember, molar mass of substance is the amount, molar mass of any substance is the mass of 1 mole of that substance. So remember, if I put 2 behind magnesium, it becomes now 48. That's 2 moles. But molar mass is just mass of 1 mole. It's just like as 12 represents dozen, 6.02 times 10 to the power 23 represents moles. And when I say now dozen mass, it's just the mass of 1 dozen. And when I say molar mass, it's just the mass of 1 mole in that context. So if you want to solve this, you now write 24 grams will contain what? 6.02 times 10 to the power 23. 12 will contain what? The answer will still be 3.02 times 10 to the power 23 for that second question. So this is it. If they are relating volume, mass for mole, if you don't know the concept of mole, how mole link between all these things, you will not get the questions right. Now I'm going to move into the next stage, stoichiometry in quantitative measurements that involves mole ratio. This one is the one that's, as we look up here, mole ratios might not be needed here, and you answer your question. This is just about connection, understanding that mole connects the two. So the next thing is that we are going to see the one that involves chemical equation, where mole ratios plays a particular important role. All right, over here, as I told you earlier, I want to demonstrate what we mean by mole ratio or stoichiometry. Remember, it is the mole ratios of the reactants and the products, the reactants and the products in a balanced chemical equation is representing the stoichiometry. So, as earlier told you, I told you earlier that if I want to cook 5 cups, maybe I love the food you cook on your birthday and it tasted well. And what are your combinations? 5 cups of rice with 3 cubes of Maggi, 1 onion, 1 spoon of salt, and 1 sachet of kitchen glory. Remember, I'm not a good cook. I'm just trying to make you understand the concept of mole. Now, it means that when I want you to cook 5 cups of rice, how you must obey this 5:3:1:1:1 to give me the same taste and quality of the food. And that is what we mean by mole ratio. In combinations in our everyday life, when we produce anything, we must obey proportions to get a desired quality. So in chemical reactions, the proportions are gotten from the mole ratios. So if here is 15, when here was 5, here was 3. So what did I do to 5 to make it 15? I automatically multiplied 5 by 3. So I must keep that ratio constant so that here will be 9. Then 3 times 1 is 3, 3 times 1 is 3, 3 times 1 is 3. So if I cook 15 cups of rice, I need 9 cubes of Maggi. That is the mole ratio, which is the same thing as 15:9:3:3:3. This will give me the exact same taste on my graduation, the same thing I got from your birthday. Now, coming to this, these are chemical equations. Let us derive the mole ratios. The mole ratios are the coefficients of the reactants and the products in a balanced chemical equation, which means the prerequisite for you to understand this is that you must learn how to balance chemical equation. The prerequisite is that we should balance chemical equation. Now, look up the first one. We have 2 chlorine atoms, 2 hydrogen atoms, but 1 here, so I'll put 2 here, and this 2 balances the equation. Coming in the second equation, sodium atom is 2, but it's 1 here, so I'll put 2 here. So I will reduce the arrow. I should be 2 here. And then 2 there requires me putting 2 here. And that settles everything. Oxygen here is 3. 1 plus 2 is 3. This is disilane, just like we have ethane. When it is silicon instead of carbon, we call it disilane. But when I write only SiH4, we call this one silane. So that when I make this only 2, it becomes now disilane. I asked a question on this equation in class 4. So here I have to balance. To make it fast, there should be rule governing this. Definitely here should be 2. And when here is 2, silicon should be 4. Okay. And that 4, because here is 2, automatically forces me to put 6 here to balance hydrogen. And when there is 6, oxygen is now 6 plus 8, which is 14. So here is going to be 7. Now, what this implies that the mole ratio of the first reaction is 1:2:1:1. Then the second one is 1:2. The coefficients is to 2:1:1. In the third one, we have the mole ratio. That's the stoichiometry is presented by 2 moles to 7 moles to give you 4 moles of silicon oxide to produce 6 moles of water. So this is what we call mole ratios. And this mole ratio implies that when you bring 1 mole of magnesium, you will require 2 moles of HCl to produce 1 mole of hydrogen gas and also produce 1 mole of magnesium chloride as salt. That means that if here becomes 2, here automatically will be 4 because 1 is to 2, 2 is to x. If here becomes 2, this is already also 2. If I provide 2 moles of magnesium, I will be expecting 2 moles of hydrogen gas. So the same thing is applicable in the second equation. 1 is to 2 is to 2. In the third one, it is very necessary because we can use this stoichiometry to solve Gay-Lussac's law of combining volume for gases. Like I told you in the class 4, I asked a question involving this reaction. So if you are unable to solve it, look at the mole ratios, which is what you need to solve it perfectly. Now, what I want you to know is that if I write 3 here now, what will this become? To follow the ratio, you just say 2 give 7, 3 will give x. You calculate it and know the actual thing that is needed. Meaning, if I make here 3, what will here become? You just say 2 give x, give 7, 3 will give us x. 3 will give us 2x times what? 21, because 3 times 7 is 21. So you divide 21 by 2. So that you get 10.5, so that here becomes 10.5 in the same ratio. So it makes sure that none of the reactants or the products are in excess. So this is it. From this, we'll now do our calculations. What I want you to be mindful is that, let's assume I ask you for the first question now, which is everywhere in your JAMB question we encounter this mass and volume relationship. If I ask you, calculate the mass produced when 6 grams of magnesium reacts with excess HCl, the mass of salt produced when magnesium, you check the 2 species I gave you. I say calculate the mass of this species and look at the given, that's magnesium. So I will follow 1 mole is to 1 mole. But if the question says calculate the volume of hydrogen gas produced at STP when 0.5 moles of HCl reacts completely with magnesium, I'm now saying find this. This is the calculated for and this is the given. So I will use 2 moles of HCl, give me 1 mole of hydrogen gas. Just know that out of this, in an equation like this, 1, 2, 3, 4, there will only be 2 related species. 2 related species are gotten from the one the question asks you to calculate for and the one the question gave you the value for, the given and the calculated for. So I want to get some things clear. Why stoichiometry involves calculations of particles in forms of atoms, ions, and molecules. Measuring the exact number of these particles directly is typically impractical. Instead, we measure masses and volumes and use the mole concept to infer the number of these particles that are involved or that are required. For instance, now, if you tell me how many magnesium atoms are required to react with 2 moles of HCl, I cannot go and be counting magnesium atom 1, 2, 3. But it has been established that 24 grams of magnesium, that is mass, means 1 mole of magnesium. And like I told you in the other section, 1 mole of any substance contains 6.02 times 10 to the power 23 particles. So if I'm able to measure 24 grams of magnesium as an element, maybe go to market and buy this ribbon, magnesium ribbon, and measure 24 grams of it, you are automatically having 6.02 times 10 raised to the power 23 atoms of magnesium. So it becomes impractical for me to go and count it this way. That's why we need this mass and volume relationship, which is controlled by mole. So we use the mole concept now to infer the relationship or to determine the particles. Or if I might ask you now, from volume, I can ask you what volume of hydrogen gas or what volume of carbon dioxide is produced when 0.2 moles of HCl reacts completely with sodium thiazocarbonate at STP. It becomes now difficult for me to determine this volume unless if I use the mole ratio 1 is to 1. I can now know what I'm expecting to get from that mole ratio. So from mole ratio, we can also determine what volume of a given reaction. So in a chemical equation, the coefficients of the reactants and the products in a balanced chemical equation represents the mole ratios as shown. Now, the importance and the applications of stoichiometry. Stoichiometry is very, very essential It upholds the law of conservation of matter, which states that matter can neither be created nor destroyed, but can be transformed from one form to another. So stoichiometry controls the proportionality between matter during the transformation processes to ensure that no aspect of matter is destroyed nor created. Stoichiometry helps in many chemical processes to ensure quality control by ensuring that none of the reactants are in excess. It helps us to identify the limiting reagent in a reaction. Hold on there. The limiting reagent in a reaction, meaning that as far as the mole has shown us that we require for this first one, magnesium is 1:2. Anytime I provide 2:2 for magnesium and HCl, guess what? But the normal reaction is 1:2, and I'm provided with 2:2. Which one is in excess? I've been given excess of what? I've been given excess of magnesium, because magnesium requires 1:2, but it is provided in 2. So if magnesium is in excess, it automatically means that the limiting factor is HCl. So the reagent in short supply is the limiting factor, while the one that is supplied in excess is said to be excess one. That is the one in surplus. So it's supposed to be 2:1, but it's now, I mean 1:2, but it's now 2:2. As you can see, I produced excess of 1 here. But the ratio is that if I must keep these two constants, 2:4 to represent 1:2. So if I provided 2 moles of magnesium, I'll be requiring 4 moles of HCl. But immediately I produce 2:2, it means that the limiting factor, the limiting reagent is HCl. It is in short of 2 moles. Okay, so these are the things stoichiometry helps us to do what? To know. So stoichiometry helps us to calculate the percentage yield in industrial processes and also determine the atom economy of a given chemical, that's of a given chemical reaction with reference to the desired product. Stoichiometry helps to determine the exact amount of reactants needed to achieve the desired outcome. These are also the applications of mole ratios in chemistry. What is a mole? We have told you what mole is, and I've given you the connections between moles. So from these mole ratios, we can determine percentage yield. We can actually know the amount of reactants we should garbage in to get the desired amount of the product in question. Now, we are going to face at least many examples from JAMB past questions. You listen to me, follow the steps I'm going to use to solve them. In stoichiometry, or mass and volume relationship, understanding when I'm solving it is not the problem. The problem is the ability to solve when you're left alone. So let's see many examples of my past question. It's every year we are going to be looking at any calculation possible. Any calculation possible. Okay? This is 2003, number 2. They say, what volume of oxygen is produced from the decomposition of 2 moles of KClO3 at STP? What volume of oxygen is produced from the decomposition of 2 moles of KClO3 at STP? They gave us in brackets that molar gas volume at STP is 22.4 dm cubed. Remember, we are going to use the chemical equation to determine the mole ratios and see how they behave in mass and volume.
Learn science for free with Sir Majesty Easy World Science. Master chemistry, biology, and physics on our YouTube channel, where we offer comprehensive tutorials, exclusive science practical demonstrations, real-world applications of scientific knowledge to solve environmental and human challenges. We also specialize in building and equipping science laboratories with quality and reliable services. Call WhatsApp +234 706 516 6217. Join us and elevate your learning experience. Stay majestic.
All right, they are talking about decomposition of KClO3. KClO3 decomposes on heating. Remember, if you heat this in the presence of manganese 4 oxide as a catalyst, gives you KCl plus oxygen gas. So you must balance this equation properly. If we introduce 2 here, we will be forced to introduce 3 here and introduce 2 here. So that's check where oxygen is 6, oxygen is 6, chlorine is 2, chlorine is 2, potassium is 2. So states of matter, this is solid, of course, this is solid, this is gas. This is the laboratory preparation of oxygen. What next? What are the mole ratios? What's the stoichiometry? 2:2:3. Now, what are the related species? Now, read the question again. They said the volume of oxygen. So you go and pick this oxygen related. Oxygen is the calculated for the volume of oxygen produced from decomposition of 2 moles of KClO3. So we are going to be working with 2:3. So among all these, our concern now is 2 moles KClO3 will produce what? 3 moles oxygen at STP. Now, watch what we are going to do. Find the units. The KClO3, did they give it to us in mole or mass? It was given in mole, and we leave this to. Assuming if it is mass, we will convert this to molar mass and times by 2. But thank God is already in mole. Whatever is in the balanced chemical equation is mole. So I will write this to is to. Are we looking for oxygen in mole, mass, or volume? Let's look again. They said the volume. So we are looking for oxygen in volume. So remember that 1 mole of a gas, in other words, gas molar volume at STP is equal to 22.4 dm cube. That means 1 mole is 22.4. Then 3 moles will give us what? 3 moles will be automatically 3 times 22.4. So
from the calculator department, 3 times 22.4, it gives you 67.2 dm cube. So this implies that I've converted these 3 moles now to volume. So instead of writing 3 moles there, I'll now write 2 moles of KCl will give me 67.2 dm cube. Then I have to add this. Now, looking at the question, they now asked us, the question was, what volume of oxygen is produced from the decomposition of 2 moles of KCl? And it happens that it is still, they asked us 2 moles will give us X. If 2 gave us 67.2, 2 will also give us 67.2. So the answer is 67.2 dm cubed. Looking at this, that is option C. So we go to the next one. Okay, this one is the calculations are everywhere. We just any calculation we see now, we handle it. Then this one is all about required to prepare. What mass of K2Cl2O7 is required to prepare 250 cm cube of 0.02 mole per dm cube solution? This one is all about knowing the molar mass. This question 16, they gave us the molar mass of K2Cl04. That's a potassium tetraoxochromate 6. What mass of it is needed is just the same mole concept. Because this concerns mole, I'll solve it. Alright. If we have K2Cr04, this is 1 mole, and the mass of 1 mole of any substance is automatically the molar mass. So, and the molar mass is 190. They gave it in that question, 194.2 grams, as you can see there on the screen, per mole. Now, what's the strength? What's the strength of the solution first? The strength of the solution required or given to us is the strength is 0.02 moles per dm cube. Now, what's required volume is 250 cm cube. Okay, so the question now is, what mass of K2Cl2O7 is required to prepare 250 cm cube of 0.02 mole per dm cube of this? So what we are going to do is, first of all, the strength is, we are going to find the strength required. 0.02 was found in 1000 cm cube. Reason is because 1 dm cube is equal to 1000 cm cube. 0.02 is in 1000, but we are looking for a one that will be in 250. So I'm going to write 250 cm cube what will be in 250 cm cube. Automatically, what happened to this? We're going to just have a 0.02 divided by 4 from the calculator department. You know what you need to do is to cross multiply. I don't have time. So 0.02 give us 0.0050. So x here is 0.0050. So what we need is this mole. And simple, we are going to use the formula that says that number of moles is equal to mass all over molar mass. So in this case, we use that N, which is number of moles, is equal to mass given all over molar mass. So we want to know the equivalent mass because they say what mass is needed. Now we have seen the mole, we are looking for this to dissolve in 250. Therefore, 0.005 is equal to the mass we are looking for all over molar mass, which is 94.2. So by now looking at this, our answer will now be mass is equal to 0.005 times 194.2. So, and this will give us times 194.2, which is 0.97. Looking at the option 0.97, option D is the correct answer to this question. Okay, so we have 0.97 grams, our final answer. All right, we go to the next. All right, here says if a solution containing 4.9 grams of tetraoxosulfate acid, they say if a solution contains 4.9 grams of tetraoxosulfate acid, calculate the amount of copper oxide that will react with it. So this is still stoichiometry. You need to write the chemical equation and balance. The reactants here is copper 2 oxide and H2SO4. All right. So we are going to write equation. So the chemical equation is going to be copper 2 oxide versus concentrated H2SO4, and this will give you copper. It's not going to be copper 2 oxide. It should be, okay, yeah, it will give you copper 2 tetraoxosulfate 6 plus water, because this is acting as a basic oxide. So balance the equation. The equation is balanced. Oxygen here is 1 plus 4, 5, 4 plus 1. Hydrogen is 2, hydrogen is 2. So the mole ratio is 1:1:1:1. So what are the related species? This is what they gave us. You are calculating for copper 2 oxide and we are looking for H2SO. They gave us H2SO4, sorry. This is the calculator for H2SO4 was given. So I will look at that question again. That should be number 4. Okay. Number 3 instead. So 4.9 gram. Yeah, calculate the copper 2 oxide that will react with it. Okay. So from the mole ratio, we just take a look at the molar masses of the two. This is, we can work in mole and later come back in mass. So this shows that 1:1. So, but molar mass of H2SO4, molar mass, if you are preparing for JAMB, it's good you know some molar masses. Like some 50 compounds, you memorize the molar masses of 50 common compounds. It shows your readiness for the exam. So this is 98, already known, gram per mole. So using N equal to mass over molar mass, I want to know the number of moles that is represented by the mass given. So the mass given was 4.9, the molar mass is 98. Therefore, N is equal to 4.9 divided by 98. This will give us a close value of 0.01. Okay, let's see. So, 4.9 divided by 98, 0.05. So it's not 0.01, sorry. So we have 0.05 moles. So, and looking at the stoichiometry, 1:1. So if here is 0.05, this is automatically 0.05 because they have equal mole ratio. So the work now is to go and convert this one now to mass because they are asking us the mass. Using the same formula, N equal to mass. This time around, mass is unknown. All over molar mass of which compound now? All over molar mass of CuSO4. The molar mass of CuSO4 will be 64 plus 16, which will give us 4 and 6 is 0. It's going to give us 80 because if you bring this one here, it's automatically 70. So 80. So here we have that 0.05 is equal to the mass we don't know, all over 80, such that the M now is equal to 0.05 times 80. So 0.05 times 80 gives us the answer, which is 4.0 grams. So the answer is 4.0 grams. Looking at the option B have the correct answer. So our answer here is 4.0 grams, which is option B. All right. Go to the next one. The other one says number 4 that follows it also says, what volume of gas is evolved at STP if 2 grams of calcium triazocarbonate 4 is added to a solution of hydrochloric acid? So we will follow the same order. We have reactants and products, calcium carbonate, and then hydrochloric acid. So we'll balance the equation. Remember, the first step is to write chemical equation and balance it. Okay, and get the mole ratios. Find the related species. So we have calcium carbonate plus HCl to give you calcium chloride plus water plus CO2. If I put 2 here, the equation is automatically balanced. So the mole ratio is 1:2, 1:1. And now the given, look at that again. The given is they give me calcium carbonate, and I'm calculating for the volume of gas evolved. So I am focused on this is the given and this is the calculated for. So I'm going to bring down 1 mole of CaCO3 will liberate 1 mole of what? CO2. Then find the units. This calcium, did they give it to me in mole or mass? If you look at that question again, it was given in mass. They say 2 grams, but this is already mole. That means I'm going to convert this mole to mass. That means I'll find the molar mass of this and times it by 1. If there is 2 here, I'll times it by 2. Remember, this one originated from the balanced chemical equation. Therefore, the molar mass of calcium carbonate is 100. You should master that. 40, because calcium is 40, carbon is 12, oxygen is 16, to be given to you in brackets. You can see there. So 40 plus 12 plus 48, 16 times 3 is 48, automatically gives you 100. So I already know that. And it will be good if you know that already to facilitate your calculations. So we have now 100 times 1 is 100. So 100 grams. This one, did they ask us to find it in mass, volume, or mole? They asked us to find it in volume. Therefore, I'll replace 1 mole of CO2 at STP is automatically 22.4 dm cubed. Remember, if there is 2 here, I'll multiply it with 22.4. Now, which one are we looking for? I'll write X here. Which side did they give me? They gave me these 2 grams. So we can find X. Automatically, you will look at the fact that, okay, we are going to see 100 or rather we see that x is equal to 22.4, of course, over 100 times 2 over 1. So looking at this, we can predict a close range. It's going to give us about 0, either 0.44 or 0.22, but let me do the mathematics. Okay. We have that 22.4 divided by 100 and times 2, 0.448 dm cubed. 0.448 dm cubed. But if you look at that option, is in cm cube, therefore you times by 1000 to convert to cm cube, because 1 dm cube is equal to 1000 cm cube. So the final answer is 448 cm cube. That's the correct answer. Okay.
Learn science for free with Sir Majesty Easy World Science. Master chemistry, biology, and physics on our YouTube channel, where we offer comprehensive tutorials, exclusive science practical demonstrations, real-world applications of scientific knowledge to solve environmental and human challenges. We also specialize in building and equipping science laboratories with quality and reliable services. Call WhatsApp +234 706 516 6217. Join us and elevate your learning experience. Stay majestic.